as I said, we're going to take a 1-week return to artificial intelligence, because in learning about complexity theory, I found out something that I really didn't know about before, and that is there's an artificial intelligence technique that we did not discuss because I really wasn't. I'd heard of it, but I didn't know anything about it, and I just didn't have the time to look into it. But basically, you remember what we talked about mostly in artificial intelligence was neural networks, which get their start from the study of the human neural network. And people said, wow, that works in brains, maybe it'll work in computers. And sure enough, it did. Well, there's something called genetic algorithms. And this is a technique where somebody said, hey, you know, this evolution works in biology. Maybe it'll work with computers. And they tried it, and it does. And I found that totally fascinating. I hope you will too when we get there, but that'll be a couple of weeks away. So we'll take a 1-week, as I say, return to artificial intelligence, and then we'll get back into mainstream biology. And at that point, what I'm going to be looking at is what they call neurobiology, and that's the biology of the brain. And I don't know how long I will go on about that. It is a topic of just amazing fascination to me, and I hope you'll find that way as well. And I'll just go on until I feel like I have said enough about it, or until you tell me to stop. Okay, so that's what the future holds. Now let's get started with today's lesson. So we're doing our final lesson on complexity theory. So here we go, and let's do a slideshow from the beginning. I didn't. How could I have not changed the title? It should say still more on complexity theory. I'm sorry. I just didn't look at that real closely. All right, anyway, so here we go. I think I lost an introductory slide here, but I'll just talk through it. What we're going to talk about today is what are referred to as complex networks. And networks are, now this is, I'm sorry, I'm going to back up for a second. I'm sure that's not my first slide. I don't know what happened to it. Okay, somehow I apologize. Somehow I have them out of order. Okay, so let me do it this way. I'll just talk through this slide and the next one, and then we can get back into slideshow mode. So here's the way I wanted to start. Many applications of complexity theory involve the concept of networks. So exactly what a network means depends on what field of study we're dealing with, but they've all got the same abstract form, and this is what I have a picture here of what we might view as an abstract network. We have these dots, and in networks we refer to them as nodes, and then we have these lines that join them, and they are the relationship between the nodes, or a more simple word is the links between the nodes. So we're going to do a little bit of terminology. The number of links that are connected to a node is called the degree of a node. And so if we look at node A there, it has 1, 2, 3 links. So we say it has degree 3. We come down here to node C. It has only one link, so it has degree 1. And we can work our way through and figure out what the degree of any node is just by counting the links. Like G has these 2 links joining it to E and F. Now, sometimes the links that we deal with are directional. We're going to, that is, you think of only going one way from one node to the other. We're going to kind of ignore that, because in that case, you sort of can replace your single network with 2 networks, one with links going one way and one with links going the other way. So we'll just let that go, because that's not really an important detail. Okay, so now let me go back to okay. A little more terminology. We say that 2 nodes in our network are neighbors if there is a link between them. So that in the network here, for node A, its neighbors are E and B and D. For node B, its neighbors are C and D. For F, they are E and G. C only has one neighbor, B. Okay. So one thing that we might notice is if we look at node A, it has, as we said, 3 neighbors. 2 of its neighbors, B and D, are also neighbors of each other because they're linked. But D and E are not linked. So A has 2 linked neighbors and 2 unlinked neighbors. Notice that C only has 1 neighbor, so it can't have any linked neighbors. F has 2 neighbors and they are linked, as does G. E has A, F, and G as neighbors. So F and G are linked, but A is not linked to any of the other neighbors of E. So when a node has neighbors that are also neighbors of each other, we say that's a clustered node. And we define this number we call the clustering coefficient by saying, like, we take node A, it has B and D, and they are linked, but then it has D and E and they're not. So it has these 3 neighbors, one pair is linked, the other pair is not. And so we say the clustering coefficient here is 1/2, because half the possible nodes are linked and the other half are not. If we look at C, the clustering coefficient is 0 because it only has the 1 neighbor. If we look at E, it has the 2 neighbors and they are linked, and that's the only neighbors it's got. And so its clustering coefficient is 1 because all the possible neighbors are linked there. So we can figure out the clustering coefficient of each of our neighbors by looking through and seeing, are they linked or not? And if they are, how many of the possible neighbors are linked, and then find that fraction. Okay, we have one more term that we have to learn about, and that's what's called distance between nodes. And that's kind of tricky because it doesn't have anything to do with the lengths of these lines, okay? When I talk about distance between nodes, it says how many links do I have to traverse to get from one node to another. So for example, node E, the distance from A is 1. but for node F, the distance from A is 2. Now, sometimes there's more than one way to do it. For example, if I want to go from A to G, I could go A to E, E to G, and that's 2 links. Or I could go A to E, E to F, and F to G, and that's 3. When there's more than one way to do it, the distance is always the shortest way to do it. So the distance from A to G is 2. So likewise, if we look at some other things here, the distance from A to C is 2, from A to D is 1. Let's take a really long one, from C to G, what's the distance? Well, I go 1, 2, 3. The shortest way is to go here, and that's 4. So the distance from C to G is 4. So these two numbers, what we call the clustering coefficient on the last slide and the distance, turn out to be important properties of the network as a whole. But what we've talked about so far just applies to individual nodes. So how do we get the terminology associated with the whole network? And what we do there is to take the average of all possibilities. So we're going to take a look at how we do that. We'll do the clustering coefficient first. Same network as before. And here I've figured out the clustering coefficients of every single node. For A, it's a half, for B, it's a half, for C, it's 0, D is 1, E is a half, F is 1, G is 1. And just to review, F is 1 because F has 2 neighbors. They are linked, so every link is used. E is 1/2 because E has A, G, and F as neighbors. F and G are linked, but F and A are not. So that makes the clustering coefficient for E 1/2. So to get the average for my little network here, I add up all those numbers, and hopefully I added them up right. I claim the sum is 4.5, 1, 2, 3, and 3, and then 3 halves is 1.5. So that's 4.5. And then I divide by the total number of nodes, which is 7 here. So my clustering coefficient for my whole network is 0.643. And now we do the same thing for the distance, except for the distance, we got to consider distance between each pair of nodes. So we have a much bigger table here than we did. So I look at each, so I start with node A, I say, okay, what are the pairs? Well, I can go from A to B, that's 1. I can go from A to C, that's 2. I can go from A to D, that's 1. A to E, that's 1. A to G is 2. A to F is also 2. Then I go down to the next node, B. Now, since I did A to B, I don't do B to A. Now, you could if you wanted to. It really doesn't matter. We're going to use this to compare networks. So as long as I did the same thing with every network, it'd be fine. But it's just less work to leave out all the duplication. So I don't do B to A because I already did A to B. It's the same thing, of course. So I do each of these, starting with B. B to C is 1, B to D is 1, B to E is 2, and so on, and work my way through the entire network, calculating distance between each of those pairs of nodes. And then I add up all those numbers. And when I add them all up, I get 43 as the total of all the distances. So take the average, there's 7 nodes, so divide by 7, and that gives what we call the average path length of the network, and it's 6.143. Now you might wonder, what's all this about? Why are we calculating these things? Well, what I want to show you is that if we make a simple change to our network, that these numbers will in fact change. And I think I had a typo here. I said adding a link from B to E, but I think I added it from D to F. Let me see. Yeah, I did. So I'm sorry that in this previous slide down at the bottom, it should say adding a link from D to F. Okay. So I add a link from D to F, and that makes some changes in my clustering coefficient. If I now calculate it, it's certainly going to make a change here at D, because D now has both B and D for neighbors as well as A. And we have a link from A to B, but we don't have a link from D to E. And so that makes this clustering coefficient 1/2. And if we go through, I don't want to drive you crazy with arithmetic, but if we go through and recalculate all our clustering coefficients, add all those numbers up, then we go from 4.5 down to 3.5. And when we divide by 7, this time the clustering coefficient is 0.5. So if we go back for a second, it was 0.643 before I added the new node, and that dropped it down to 0.5. So it certainly made a difference there. Well, what would that do to our average path length? Well, do the same kind of thing. Again, I'm not going to run through all this arithmetic. If you want to do it on your own sometime, feel free. But it does make changes to our network to put in this extra link. For example, I've now got a different way to get from A to G, and a different way. Now here's a big one, for a different way from C to G, from C to F rather, because I can now come 1, 2, 3, whereas before I had to go 1, 2, 3, 4 to get here. So that when I add up all these new distances, I get 38. And I divide that by 7, and it takes my average path length down to 5.43, whereas before it was 6.143. So dropped it almost 1. So just adding 1 length made a fairly large difference in the average path length. Okay. So what do these properties have to do with networks? Or why would we care about them? Why would we want to work them out? And to explain that, we have to go back and look at some work done by a couple of mathematicians back in the 1990s. A guy named Duncan Watts and Stephen Strogatz. At the time, Duncan Watts was a PhD student of Stephen Strogatz's. And they were studying networks. And they defined a kind of network that they called a small world network. And that name comes out of networks being used in the terms of like what we think of as a social network. You might have in your life had the following kind of experience. You might have joined some organization without knowing many people in it, just because you were interested in it. And to your complete surprise, you find out that someone you know really well is already a member of that organization. And so on finding out something like that, you say something like, it's a small world. So that's where the term small world network comes. So what Watts and Strogatz figured out is that if you have an unexpected link, that gives you some important information about your network. It tells you something about the structure of it. And that in fact, just a few randomly chosen links that you didn't expect to be there can drastically change these numbers that we calculate for a network, the average path length and the clustering coefficient. And what they noted was that this kind of thing that they called a small world network was a network that tended to have a small average path length and a large clustering coefficient. So in their paper, they gave 3 examples of small world networks. The first one was something that they invented. Now, this is one of those weird philosophical things. I say they invented this network. They didn't actually invent it. It was already there. It's just that nobody had ever discussed it before. Some of you, I'm sure, know about the Internet Movie Database. That's a database of just every kind of movie that's ever been. It goes back and includes silent films, comes up, includes all the, as soon as a new film is released, it goes into the Internet Movie Database. But it also includes episodes of TV series. It includes film school projects. Even includes some amateur films, some that were never actually released to the public, but just some guys got together and made their own movie for the fun of it. And it came into being originally by a bunch of movie fans who wanted to be able to track information about movies more easily and knew something about databases. Said, well, if we create this database, all we have to do is new movies come out, we have to add them in here, and then we can keep track of things. So it was actually created by, and I don't even know who the people were, but some group of movie fans created it. And then Amazon came along and said, wow, this thing is really cool. It'd be great for us to own it. So they bought it from them. So it's now owned and maintained by Amazon, which means that there's no problem keeping you up to date because they certainly got the people to do what it needs to keep that thing current. So if you look in that database, you can find just about every movie that was ever made. You can find who all the cast members were. You can find who was the producer, who was the director. You find like all the members of the crew. Just, you know, if you just sat and watched the credits of a movie, all that information goes into the Internet Movie Database. So what Watson Strogatz did is they said, well, that means that if we take any movie actor, we can look through all the movies that he's ever been in and see who the other cast members were. And so we can establish a relationship between 2 actors by saying that they are linked if they were in 1 or more movies together. Okay. Well, that results in a huge network, of course, because there have been lots and lots of movies, lots and lots of actors. And in a lot of cases, you know, we get actors that have been in the same movie together. Now, Watts and Strogatz said this is a small world network. And in fact, this database is actually the source of a game. Again, I'm sure some of you have heard about the 6 Degrees of Separation from Kevin Bacon game. This is a little challenge, kind of like a trivia game you play with your friends. They pop up with somebody suggests an actor's name, and then you try to find a path to the actor Kevin Bacon by traversing through links in this network. So if this actor appeared in a movie with Kevin Bacon, then bingo, it's there. But if he never did, then what you do is you look at all the other actors that appeared in movies with him and see if any of them ever appeared in a movie with Kevin Bacon. And if not, then you take all the actors that came up looking through that list and you go through them. If you want to play this game, There's a place online. I'm sure there's more than one. I found this one, uh, oracleofbacon.org/movielinks.php. And you can play it there. And just for fun, we're going to take a minute because it amazed me when I did it. So I'm going to stop sharing this for a moment. And I am going to share. Where is it? Oh, I've lost it. Oh, let me bring it back up. Okay, now let me see. There. Okay. So this is, you might not be able to read that. That's Kevin Bacon's name. And the idea is uh, you type in here the name of some other actor, and this will give you the number of links that you have to go through to connect that actor to Kevin Bacon. Uh, and I thought, well, I'm really going to trick this thing. And so I said, who's an actor I can think of that I bet's not connected to him at all? And I went back to my childhood, back to the cowboy movies I used to see. I said, well, what about Gene Autry? I bet he's not connected to Kevin Bacon at all. And you click find link. And by golly, look at this. Gene Autry appeared in a movie called Hollywood in Uniform with Eddie Albert. And Eddie Albert appeared in a movie called The Big Picture with Kevin Bacon. And so, in fact, they are related. It only takes 2 links. I'm going to do one more, and then I'm going to, let you, if you want, you can play with this at your leisure. My next thought was, okay, Gene Autry, that's going back a while, but it's not really way, way back there. What about if I go back to the days of silent films? And so I remembered a silent film actress named Clara Bow. And I said, I'll bet she's not linked to Kevin Bacon. And you click the link. And look at this. She appeared in a movie called Helen's Babies with somebody named George Reed, who I have no idea who that is. He appeared in a movie called Going Places with somebody named Larry Williams. I don't know who that is. But Larry Williams appeared in Apollo 13 with Kevin Bacon. So there's only 3 links there. So the idea of the 6 degrees of separation is that if you take any actor, it will be true that it'll take you no more than 5 links. They're no more than 6 apart. Now, that's not actually true. If you really work at it, you can find really obscure actors that you can't connect to him with just 5 links. But you really got to try hard. Almost any actor who anyone has ever heard of will, in fact, turn out to be linked by no more than 5, and a surprising number are linked with only 2 or 3 links. I spent about a half an hour on this, just typing in every name I could think of, and I was just amazed at how many people are so closely linked. Okay, let's go back to our presentation now. So I'm going to stop sharing this, and I'm going to share the presentation again, and let's continue. Now this happened to me once before as well. Okay, I know what I can do here. Oh, I know what I need to do. Click there. Yeah, there we go. Uh, Now, I said that they had three examples of small world networks, and the other two are totally different from the movie one, and they're also totally different from each other. The second one uh, is the neural network of a nematode whose name is the C. elegans. The C stands for some long Latin name that you always see it abbreviated C period, so I just did that. Anyway, a nematode is a very, very, very tiny little worm, so small that if you put 25 of them end to end, you would have only an inch. But it has a tiny little brain that has about 300 neurons in it. And because its brain is so tiny, has so few neurons, it's the only complete neural network that's been mapped out. Biologists have actually gone in there and figured out the connections between every single neuron in the nematode's brain. And it turns out that this network is indeed, if we use our definition of having a short average path length and fairly high clustering, that it is a small world network. It just seems like you could think of no reason why it should be, but it in fact is. The last example that they came up with was the Western States Electrical Power Grid. That's the power grid that connects all the states on the West Coast, plus the mountain states. Now here, the nodes are the power plants and generators, and the transformers, and the switches that are in that power grid, and the links are just the power lines that hook them up. And once again, there's just no reason in the world why you would think there would be any relation between that network and the neural network of a nematode. There just doesn't seem to compute that there's some connection. But there is, and this is also a small world network, in that it has a short average path length and a large clustering coefficient. Now, since there were a lot of other networks have been shown to have this characteristic of being a small world network. Now, the human neural network is way too complex to be mapped. Remember, nematodes have 300 neurons. We have 100 billion. So nobody's ever going to map the human neural network. But there are, in fact, some small parts of the human neural network that are called subnetworks that have been mapped. And those indeed turn out to be also small world networks. Okay, so now I want to look at a really, really huge network. What's possible, I can't verify this, but this may be the biggest network that humans have ever come up with. And that network is the World Wide Web. Now, the nodes in the network are the web pages, and the links are the hyperlinks that allow you to get from one page to another. It's estimated currently there are about 60 trillion. So that means like 9 zeros, 60 followed by 9 zeros, 60 trillion web pages. I looked around, I could not find an estimate for the number of hyperlinks, but it's got to be bigger than that. I mean, most web pages have links to several other pages. So it's got to be just way up in the trillions. Now, the most interesting thing about the World Wide Web, if we think about it as a network, is that it's not planned. You know, for example, that Western States Power Grid, that wasn't planned to be a network, but it was planned. It was, they didn't just, you know, go around and start throwing up power plants. They did it for reasons. But the World Wide Web, I mean, when it started, nobody had any idea what it was, that it was ever going to be anything. It was first just something for scholars to use so that they could easily look at each other's work. But, you know, it sort of got out of that cage and went and took over the world. So it really is an unplanned network, and as such, it has a property, which I don't know whether you'll be surprised by this or not, but since this thing just happened, again, it sort of shows you that there's something going on with complexity theory that has some enormous effects. The thing that turns out to be true about the World Wide Web is this. If we look at the number of links that are associated with a web page, sometimes there are some web pages that only have one link. Not a lot, but some. There's some that have two. There's some that have three. And of course, there's some that have thousands and thousands of links to them. If we were to draw a graph in this way, if we were to say, okay, how many web pages have only one link? And we'd come up with some number, and we'd plot a graph point and say, oh, how many have two? And we'd add that up and plot some number, and then go out and say, how many have 150,000? And we'd plot that number. How many have 1.5 million? Plot that number. What we'd end up with is a graph that would look something like this, which is very similar to graphs that we looked at last week. That is that the number of web pages that have just a very few links can be very, very, very large. As we get out to pages having more and more links, then the number of such pages gets smaller, but it's always there. It doesn't go, it doesn't just sort of go away. When you get out to web pages with, say, 2 million links, there are some. And if you go to 5 million links, you'll find some. And so this has exactly the same form of what we called a power law graph last week. And it turns out that Google, just a little brief history, when I first started using computer searches, it was actually before there was a Google search. There were things like Alta Vista was a big one, and there were some others around. And Google search came along, and at first, Google search was pretty much like all the other search engines. What it would do, it would build an index of the web so that if it could take the words that you used in your query and look them up in the index, and it could find all the pages that contain those words. But that was where the problem was when I said pages. If there was only one such page, fine, and say, here's your answer. That's what you're looking for. That's all we got anyway. But that's very seldom true, because the web is, there's 60 trillion pages out there. So chances are there's lots of pages that have those words you're looking for. And the original Google search, like everything else, just sort of returned a list of pages just in the order that it found them. So you might find, if you did a search, you'd get back a list of, 100 pages maybe, and then you'd have to scroll through that, and number 85 would turn out to be the one you really wanted. And that made the computer search, a less than fun thing to do. But then a couple of guys at Google came up with this idea. They said, hey, while we're out there on the web building our index, let's add something else. for each page, let's calculate how many links go to that page. And so now you type in your search query, and it goes out to the index and pulls in all the pages that contain all your words, and it looks at the number of links that each one has. And it shows you the one with the most links first, and the second most link second, and so on. And the reason it does that is the simple assumption that if lots of people have linked to a page, that probably means lots of people want to find it. And you're a person who wants to find it, so chances are that's the one that you want to find. And, you know, pretty much that's true. It's very seldom that I go looking for something, and it may not be the first one, but it's pretty much always in the first two or three. So there's one more question you might be thinking about the World Wide Web. We talked about these small world networks. And our question might be, is the web, the World Wide Web, a small world network? It turns out there's no way to answer that question. And the reason that's true is that we pointed out 60 trillion total web pages. That's a lot, but that's not the problem. The problem is that about 380 pages a minute get added to the web. So if we're out there trying to calculate the average path length and the clustering coefficient, we can't get it done. By the time that we have finished our calculation, a bunch of new pages and a bunch of new links have been added. So now our result is no good anymore. You know, it's just, you know, it's a fascinating question, but as best I can tell, there's no way to answer it. Okay, I want to show you one more thing, and that is I discovered an advantage of doing these things from home. That is, I've got access to things that I don't have access to when I'm at the senior center. And did I lose this thing? Well, I'll just start again. Okay, I'm bringing up a piece of software, and I'll show it to you in a minute. And it's called Nematode. And what it does is it lets you do all kinds of interesting, fun math stuff. So let's get a nice big picture now. Let me share my screen again. Okay. I'm going to assume you don't really want to know all the details of this. You just want to see me do something with it. If you're interested in it, if you Google Nematode, you can find out lots and lots about it. You can download your own copy if you want. It's free. But what I'm going to do is we're going to illustrate some of the points that we were just talking about. And so to do that, I'm opening the Nematode models library. And I'm going to the network models. And here is a model called a small world network. And so I'm going to open that. Takes a minute for it to get loaded up. Okay. And what this is going to do is we're going to be able to show how modifying what we call a regular network can turn it into a small world network. So I want to do one thing that I'm going to make it a little bit bigger. So I'm going to say, let's make ours, instead of 40 nodes, let's make it 60 nodes. That's good enough, I think. Okay. And then what I'm going to do is I'm going to click this setup button. And this shows the original network. Now, what they've done here to make it easy to see is they put all the nodes in a circle. Now, what you can't see right now is what are the connections between the nodes. But if I click this highlights button, that I can. If I select any node, notice though, this node turned red, and the two nodes on each side of it are blue. So that's their indication of what the current links are. The red node is linked to its two nearest neighbors. Now down here we get some information. It says that the clustering coefficient is 0.5 and the average path length is 7.75. Now if you can read very well, you see it says for 60 turtles. NetLogo was based on a language called Logo, which existed a long time ago, which dealt with something called turtle graphics. And anything that's a shape in that logo was called a turtle. So that's why they refer to these nodes as turtles here. So just a little aside on that. But anyway, if we pick out any single node, we'll see those links that now exist. Okay, each node is always linked to the two on either side of it. Okay, now I'm now going to click this button that says Rewire 1. What that's going to do is it's going to change the links on a single node. And there we go. Now notice the clustering coefficient actually went down a little bit, but the average path length also went down. And if I now click here, you'll see that this node, which got rewired, is still linked to those two, no longer linked to the one that's physically closest to it, but now still to the other one. And then it has this random link coming down here. If I click Rewire 1 again, then another node gets rewired. And we see again what's happened with the links. And we see our average path length has come down some more. Now, what I can do down here is I can rewire a whole bunch of nodes. We've got this thing called rewiring probability, which is a probability that any node here will get rewired. So as it goes to each node, it's set now at 0.3. So there's a 3% chance that it'll rewire it if I click rewire all. So let's just do that. And we see that a lot of nodes have now been rewired, that now our average path length has come all the way down to 3.25, 3.256, I should say. And so what this is showing us is that as we put more and more random links in, that this network that started out to be very, very regular is now much more like a small world network. Okay, so I just wanted to show you this tool. It's really handy, and you're going to see it again. I realize today is, may not be as meaningful as it will some other time, but I thought I'd go ahead and introduce it today, since it would give us one way to look at a visualization of what we had talked about.